It's really a great pleasure to have Mercouri Kanatzidis with us today. Mercouri is a professor at Northwestern, as you can see, well, somewhere on here. Maybe not, actually, you can't see it anyway. But let me tell you, not surprisingly from his name, you can tell he's from Greece, right? He was born in Thessaloniki and got your bachelor's degree at the Aristotle University of Thessaloniki. I'm sure I'm blowing it, apologize. And a PhD from the University of Iowa, and then he was a postdoc at the University of Michigan, and then at Northwestern. And he's a solid-state chemist, as you'll hear very soon. And he started out his academic career at Michigan State University and rose up through the ranks there, and then moved to Northwestern, where he is now the Charles and Emma Morrison Professor of Chemistry. And he's had many awards, all of the beauty prizes that young chemists tend to get, and then also he's been a Guggenheim Fellow and a Humboldt Fellow, and so he's there's a long list, and I won't go through it. So please join me in welcoming Mercouri.
Okay, hopefully you can hear me in the back. Is it okay? Can you hear me? First, I'd like to thank Emily and you for inviting me here. I had a great day. I really enjoyed my discussions with the faculty and the students. I heard some great science that is going on here. So thanks for the invitation. It's really great. Today I will talk about my thermoelectrics program, and I assume that most people here don't do thermoelectrics, so I have a little bit of an introduction. Before I forget, I would like to give credit to several students and postdocs who have been outstanding in this project. John Androulakis in particular, Lidong Zhao, Stephen Girard, Kaniska Biswas, Yasul Lee, and Rachel Kokos, who have been working on this project, and several others before them. Also I'd like to thank a whole bunch of collaborators. Doing thermoelectrics is sort of the ideal type of project to do collaborative work and have synergies between a variety of people, chemists, material scientists, electrical engineers, physicists, and so on. And so this is a motto we go by at Northwestern. And here's a bunch of, it's a long list, but particularly I would like to highlight Vinayak Dravid, who is an excellent transmission electron microscopist, and I will show a little bit of his work today, as well as Tim Hogan, who is at Michigan State, Art Freeman at Northwestern for some calculations. Here's a short outline. I will say a little bit of basics of thermoelectrics. Sort of the general strategy of how to go about looking for a good thermoelectric and how to make it better, and then the nanostructuring concept, which is essentially a new paradigm in this field. So thermoelectrics is based on a property called thermopower. That is a very old property discovered way back in 1821 by Thomas Seebeck, a German physicist, who first observed that if he had a copper sample, a copper wire, and he heated one of them, he observed a current going across. And remember, this is 1821. Okay, this is not. There's no Keithley. The Keithley company has not been invented yet. You cannot get a voltmeter or you cannot get an amp meter and measure these things. How do you measure, how do you prove that there is a voltage across a sample in 1821? And so here's how you do it. You have the magnet. And so the magnetic field goes through and the magnet responds, and you have proof that you're having current here. I think it's ingenious. It looks trivial now, but it was ingenious then. He thought, he misinterpreted the result at the time, but nevertheless the result really tells you what it is that this phenomenon can do. You can have a direct conversion from heat to electricity without any intermediaries without turbines, without anything. It's a pure solid state effect. And this is, of course, the reverse, where you use it as a cooler by applying power. You generally need a p-type and an n-type material. You put them in series together, and thermally they are in parallel. And so both are necessary. They don't have to be the same, but they can be. So this is an all-solid-state device, has no moving parts, and makes no noise, and it's proven to be highly reliable. So the name of the game here is shown here. You have heat, you pass it through the device, a fraction of it is converted to useful electricity, the rest of it is thrown away. And therefore, the goal is to maximize the fraction of electricity. That's the efficiency, how the efficiency is defined. So something like this can have a lot of applications, especially where you have waste heat, but not only. So some of the holy grails, the big applications, are in automobiles and vehicles, over-the-road vehicles, cars, and so on, where there's a lot of exhaust, there's a lot of energy density, and also 3/4 of it is thrown out the pipe. So there's a lot of interest there. But also other places, like utilities, where they're burning coal or oil, chemical plants, the glass industry, the bricks industry, and so on. There are opportunities where there's high-grade heat to make a difference. Of course, NASA is responsible for making these things popular and also showing that they are reliable and they can last a long time by deep space missions. For example, using plutonium as a hot source, and then a thermoelectric that can give enough power, let's say 250 or so, or 300 watts, to power a spacecraft in missions beyond Mars, where there's not enough sun. And there are a number of other applications as well. And the list can be very long, actually. It's amazing how creative people can be once they know about thermoelectrics. So will thermoelectrics save the world? Everybody has an energy picture and so on with the different technologies. And I'm not here to say that thermoelectrics is going to save the world. I don't think it will. But let me sort of put it in perspective. This is an energy flow that you may have seen before. And it tells you where our energy sources come from and who is using them. So we have coal, we have natural gas, we have crude oil and petroleum, we have nuclear power. And these are the fractions. So nuclear power is about 8%. Renewables is about 6%. And in fact, if you take the renewables and you blow them up, then you have solar, about 1 or 2%, biomass, geothermal, hydroelectric, wind. All together, they make the 6%. Now, in the end, the users are residential, commercial, industrial, and transportation. And between here and there, about 65% of the energy is wasted. Now, if you can recover some of it, not all of it is recoverable, by the way, but if you can recover some of it, say 5 to 10%, the whole thing could amount to about 6 to 8%. So all the renewables and nuclear combined. So that's where they fit. It can make this whole system more efficient by harvesting some of the heat that it is wasted. So it's this sort of a perspective on this. All right, so how can you, so this is a materials program, so these thermoelectric materials have to be found, and how can you tell a thermoelectric material is any good? And that is here's this figure of merit called ZT. This is essentially a unitless number that says the figure of merit is proportional to the conductivity, the thermal power, which I just defined it for you, the square of that, and divided by the total thermal conductivity. And the whole thing is multiplied by T to make it unitless. The numerator of that is the power factor. It's also a good value to look at. So you see here you need high conductivity, high thermal power, and very low thermal conductivity. And the reason you want low thermal conductivity is you want to maintain that delta T. If the thermal conductivity is high, you're going to equilibrate, and you're not going to be able to use it. So you need to make, you need very low thermal conductivity. And this is how the ZT relates to efficiency. So there's no upper limit to the ZT. Basically, the ZT defines the fraction of the Carnot fraction that can be used. So this is limited by thermodynamics, as it should be. And this is how ZT, for example, relates to efficiency. So for a hot source at 800 Kelvin, cold at room temperature, if you have a ZT of 1 average, then your best device would be about over 10% efficiency. If, however, you go up to the 2s, then you go closer to the 20%. These are anything between 10 and 20% conversion efficiency is huge here. It's very significant. So the higher the ZT, the better the efficiency is going to be. But here's the problem. These properties are not independent. You raise one, you lower the other. They're contraindicated. So the power factor. So let's look at first as a function of carriers. So a material that you can change the carriers, the conductivity, the more carriers you put, the more conductivity you have. However, the Seebeck goes down. It's predicted to go down. Also, the more carriers, you get more electronic part. So there's somewhere in between, there's a sweet spot for the power factor, which is the product. And you need to find that sweet spot, and hopefully that would be high enough to make it worthwhile. So all the fuss in thermoelectrics is about optimizing these contraindicated properties, which is not easy. So for the beginners, we published a few review articles in the last 3 years, and they're shown here. They review the field. This was published in Angewandte Chemie. This was published in Chemistry of Materials, and this was published in Advanced Materials. So you can start from there and see the broader picture. So how do we go about thinking about thermoelectrics and optimizing them? And so what makes a good thermoelectric? If you take all the relevant materials parameters, solid state materials parameters that maximize the ZT, you can come up with this equation. The Z maximizes, maximum ZT is proportional to something called gamma, which is essentially the band degeneracy, and that has to do with the crystal structure of the compound, the crystal symmetry. That's here. It has to do with tau, which is the scattering time. So you need long scattering times. That means high mobilities. You need a high anisotropy in the effective masses in this fashion. If the good direction is the flow direction is the MZ, the Z direction, then the effective mass along the Z direction should be small, and the others should be large. And of course, the lattice thermal conductivity going here. So we need. So how do you? What does a large gamma mean? So here's a cartoon of an electronic band structure, and if the symmetry is high and you have a band extrema at particular places in the Brillouin zone, you can get high gammas. For example, if you have cubic structures, rhombohedral structures, and so on. But at the same time, if you have complex electronic structure, where it gives you multiple pockets, say, in the conduction band, in red, or multiple pockets, hole pockets, in the valence band here, that gives an additive effect. In other words, every pocket contributes its own thermal power, its own thermoelectric activity, and it's additive. And then, if it's high symmetry, then it's multiplicative because the gamma can be high. So, for example, it's better to have the multiple pockets than to have a single pocket for a given number of electrons. Let's say if you had 100 electrons and you put them all in one pocket, your thermal power is not going to be as high as if you divided them 33, 33, 34 and had this situation. You can calculate mathematically that this would give you a higher power factor than that. So it's additive. it's sort of equivalent to doing this. You want carriers, lots of carriers. When when you have too many of them, they're congested. They cannot travel. Their mobility is low, so you have slow traffic. In thermoelectrics, as I said, you need single doping. You need all N-type or all P-type. You don't want both in the same material. And so you want carriers going only in one direction. You don't want carriers coming back, because that cancels the effect. So then you want all these carriers to be divided, a few at a time, in multiple lanes, so that they can have a high mobility. And this is the correct system. So what does that mean? I'll come back to that in a second. So, first of all, it means that we're looking for such materials. So what are the leading materials today? There's a number of them. I start from the top, sort of the oldest material, bismuth-telluride, antimony telluride, ZT of 1 at room temperature. This is still the best material at room temperature. Lead telluride, about 0.821 at high temperature. This is an old material. This tags material, that was the first one of the oldest material that had ZT over 1, because 1 was thought to be some sort of a barrier for a long time. Half-Heusler alloys, there's a community working with them. Best ZT of about 0.8 at 900 Kelvin. The Skutterudites that have come along lately with a ZT of about 1.4, 1.5 at high temperatures. These are all pure phases, single compounds, magnesium silicide, and then the nanostructured materials that my group is doing as well. and sort of I will focus on this the rest of the talk here. And so let's take lead telluride. And lead telluride comes close to the description I gave you with the multiple pockets. It's cubic, so it's very high symmetry. And its band structure looks like this. It has two valence bands and one single conduction band. So when you dope with P-type, you have the potential of actually getting both involved in transport. Band gap is nice and small. And also the multiplicity of these points in the beryllium zone, the L point and the sigma point, they have high gamma. And so it can give high power factor. So we were looking at this. Let me calibrate you a little bit on thermal conductivity, what we're looking for in thermal conductivity. The best, of course, the best thermal conductor that we know is diamond over here. And in these units, watts per meter Kelvin, you're talking about 1,600 watts per meter Kelvin. On the other end of that is something like wood, about 0.2 watts per meter Kelvin. And copper is about 400 or so in metals, several hundred. And lead telluride is about 2.2. That is amazing. It's much closer to wood than it is to any of these things. And so we're looking for materials that will come close to this value rather than here. Otherwise, you have no chance of having anything that would be worthwhile. So some time ago, we were playing with this system because we thought we will take, it's cubic already, it's the lead telluride structure, and then we will take lead atoms out and replace them with silver and antimony atoms. So lead atom is 2+. You take 2 lead atoms, that's 4+, and you put 1 silver, which is 1+, and 1 antimony, 3+, so your average is 4. So you can actually make this series of compounds, which we call LAST, lead, antimony, silver, tellurium, with any M you want. So basically you are disordering antimony and silver atoms on the lead sublattice. We thought this would be a good thing to lower the thermal conductivity. And then you can do this as a function of M, and you get a smooth variation of the unit cell, which suggests this Vega's law. So Vega's law is used as a diagnostic of having a solid solution, of having this thing actually doing what we're supposed to be doing. It's dissolving in there, and the lattice parameters are changing smoothly. This thing surprised us in that the thermal conductivity, the lattice thermal conductivity was very low, about 0.8 watt per meter Kelvin. The parent compound, without any silver or antimony, was, as I said, 2.2. And based on theory, because you can predict the solid solution behavior, based on theory, we could have expected about 1.4 to 1.5. Instead, we got 0.8. That was surprising that we got a low value. And this gave rise to a very big jump in ZT to the record territory of about 1.5 for N-type material. That was intriguing. And so why was the thermoconductivity low? So we went into the guts of the material and looking at the atomic scale and the nanoscale using transmission electron microscopy, and we were surprised to find that this thing, even though it was following Vega's law, was not homogeneous. It was inhomogeneous, and it had several other phases that had precipitated in the matrix. So we had nanodots precipitated in a matrix. They were quite coherent. And we thought that these things may be linked to the low thermoconductivity. We didn't know at the time. We call this type of precipitation here endotaxy by analogy to epitaxy because it is coherent and there's lattice matching. It's trying to lattice match in all directions. And so we think this is significant in the properties. This was a discovery. And it was surprising because it was also important because later it changed the way we think about these types of materials. But we had to figure out ways to actually make these things on purpose. And we came up with 3 different ways based on spinodal decomposition, nucleation and growth, and liquid encapsulation. So why does it do that? It turns out it does that. One is the difference in lattice parameters between, let's say, if you write this as such, you have two different phases, essentially mixing 2 different phases with large difference in lattice parameters. That could be a driving force for phase separation. Another driving force could be that the fact that a 1+ and 3+ pair for silver and antimony cannot really disperse very well because it's attracted in a sublattice of 2 pluses. It's like having a sublattice of 0 and having a +1 here and -1 there. So they are attracted. So as these things cool from the melt, to make a local average of 2+, silver and antimony have to find each other locally nearby. So this is a nucleus of a second phase, and then it could grow. So there is a thermodynamic driving force, it appears, for these things to phase separate. Are they stable? So because they are thermodynamically driven, they are very stable. You can take these things, you can anneal them at 600 degrees for months. And not only they don't go away, you can examine the material before and after, and you find no difference. It gets better because you anneal out some of the other defects, and you get higher mobilities, and therefore higher power factors, and higher ZTs. So they're very stable. So at that point, we thought this is why the thermoconductivity is very low. Vega's law is not a good way to use as a diagnostic that you have a solid solution. So we published this somewhat provocative paper in JAX that we ended up with the myth of solid solution. So we became suspect. Everything became suspect at some point. Anything that's a solid solution, how do you know it's actually a solid solution? Well, it follows Vega's law. You have to show TEM, and you have to make sure that the TEM is clean. But we still had some doubt in our mind. I mean, how do we know that these things are responsible for scattering phonons, more so than theory would predict for the solid solution? And so we needed a system that came in 2 flavors. It was identical chemically, it had the same composition, but it came in 2 flavors. One flavor was the true solid solution, and the other was the nanostructure. Everything else should have been the same. So we found this system, lead telluride, lead sulfide. And this is the phase diagram. And so this is 100% lead telluride. And if you start adding sulfur, at first you have a region that appears to be a solid solution. And then you enter a precipitation region where lead sulfide precipitates. And then another region where you add more, and it's this spinodal decomposition region. We managed to quench a melt from here, from the liquid down to the solid state down here, and show that it was a solid solution. It didn't have time to phase separate. We analyzed it by TEM and found no evidence of phase separation. However, it's metastable because according to the phase diagram, it should be in the nucleation and growth region. So we took that quent sample and back up, we annealed it. And if you anneal it, it precipitates these things, lead sulfide, all over the structure of the lead telluride. So if you raise the temperature, then you have these nanocrystals spontaneously form all over the place. So now we have the two flavors, the solid solution and the nanostructured material. And so we were able to do the definitive experiment. So this is the quench material, the solid solution, that shows a good TEM with no evidence of second phases. And when you heat it up at about 500 degrees, you end up with a nanostructured material. So we measured the lattice thermoconductivity at different temperatures as this thing was heating up. At room temperature, the solid solution already has a very low thermoconductivity here. You see it's 0.9 or so. And it's down from 2.2 to 0.9. So that's this disorder, this lattice, this alloy scattering works very well. However, when you raise the temperature and these things begin to form, the thermal conductivity collapses by another 50% into this area, well, 0.4 to 0.5. And then it stays like that in subsequent cycles. So to us, this proved that it is the nanostructures that actually are scattering these phonons very effectively. So then you can take that and you can do doping. Here we did N-type doping using lead chloride. The chloride substitutes the telluride in the lattice. It has one extra electron. It makes it N-type. And then we were able to optimize with different doping levels the power factor. And using the very low thermal conductivities here, we were able to get ZTs of about 1.4 or so at high temperatures. So this is a great thermoelectric system. So having done that, we wanted to see what happens then with other nanostructures. Especially we wanted to go on the P-type because, as I told you, the electronic structure is more favorable. It has two valence bands. So we chose strontium telluride, and this is the lattice parameter. So it has a little bit of difference here. And we also used other ones, magnesium, calcium, and barium telluride. You can take that, and here's where they lie. So this is the lattice parameter of lead telluride and the band gap. And these things all have very, very large band gaps. Some of them are bigger, and some of them are smaller. So you can make these things, and you can add small amounts, 0.5, 1, 2% in lead telluride. You take the X-ray diffraction pattern, and it's clean. Only rock salt structure. However, the lattice parameters respond. So as you raise the strontium telluride, you raise the lattice parameter. So that's good. And then again, it's Weger's law. It tells you that it's taking up, it's dissolving in the lattice. So here's what these things look like. You can cut the samples and to make measurements. These are made by cooling melts and making ingots. So you can also add sodium. If you want to dope lead telluride P-type, you can add sodium. It has one electron less. It occupies a lead site, and it gives you holes. So if you add sodium, then you can make highly conductive samples. So this is room temperature. You get over 2,500 Siemens per centimeter. These all have the same sodium amount, so they have the same number of carriers, and they have a similar conductivity. So that's good behavior for hole doping. And here's what we found. This was our very amazing result for us. We measured the carrier concentrations, and they were more or less between 4 and 6, 10 to the 19th here for this amount of sodium doping. And then we took samples that had the same carrier concentration and compared them to a sample that had also it was pure lead telluride with the same carrier concentration, but no strontium. From the carrier concentration and the conductivity, you can get the mobility, and so here's the mobility, and here is the three samples that have the same carrier concentration, but they have, one is pure, one has 2% strontium telluride, and one has 1%. And they have the same mobility. So in other words, this system doesn't know strontium telluride is there. It acts as if it's pure. This was surprising because in general, our experience is when you put something in lead telluride or in any semiconductor, mobility gets degraded because you get scattering off of the lattice sites. But here, we pay no penalty in mobility. And that's a very good sign, and I'll come back to that because this is critical. So thermal power, this is the thermal power of the system. It's positive, so it's P-type, that's what you expect. And what is characteristic about this is the very sharp rise of the thermal power from low values at room temperature to very high values at 800 degrees. And this very sharp rise is, that's where the two bands come in. Both are contributing and you get the sharp rise. If you only had one band, the rise would have taken this path here. So the second band is contributing as well to get the very high thermal power. And that, and along with the high mobilities that give us high conductivity, we got a very high power factor for these samples. And whether they have 0.5%, 1%, and 2%, we have a similarly high power factor. So the thermal conductivity is lower than lead telluride, lower than lead telluride, but it drops as you add more strontium telluride. So the lowest, this is total, the lowest value is for the 2%, and it falls below 1 watt per meter Kelvin. This is total. If you extract the electronic part, then you get these numbers, which is about 0.4 to 0.5 watt per meter Kelvin, one of the lowest lattice thermal conductivities for lead telluride. So you take the lead telluride value, which is the dotted line, and you bring it all the way down here. At the same time, the power factors are more or less the same, as if the lead telluride didn't know the strontium telluride was there. So this is a great combination. Now let's look at the transmission electron microscopy. So even though, again, the X-ray diffraction tells you it's Vega's law system, it's smooth and well behaved. If you look at the TEM, this is what you see. It's inhomogeneous. You have, it's full of these nanodots. Whether you have 1% or 2%, you have essentially the same size distribution, only you got more of them in the 2%. If you analyze this, if you count them, you find more. So this is the blue. This is the size distribution from about 1 nanometer to about 15, and it's about the same size distribution, but you got more in the 2%. You might say, oh, okay, of course I get more because I get 2%, but it's not necessarily true, or it is not necessary that you're going to get more. You can get the same number, only bigger. If it's the same number, only bigger, you get less interface area. It's the interface that scatters the phonons. So you need to maximize that, and when you do, you get the maximum effect. So if you get bigger particles, and they're equal to that or even fewer, then your thermal conductivity begins to go up again. And that's what we observe. Another remarkable thing here is, even though this looks like a messed up picture, you got these nanodots all over the place. You take an electron diffraction pattern from these areas, you see a single crystal. These are aligned endotaxially. These are single crystallites of strontium telluride having precipitated in lead telluride, and they're endotaxially aligned, all of them in the same direction. So you get no splitting. This is a single crystal. So the density of this we estimate about 10 to the 12. So why doesn't the mobility go down? So we have the thermal conductivity of the nanostructure is much less than that of the pristine material, so that's good. We're scattering the phonons. But the mobilities are the same between the two. So here's how we explain that. Both are tellurides. Strontium telluride has tellurium band. One is wide gap. Strontium telluride is a wide gap material, and the matrix is a narrow gap material. But both have, in their valence bands, tellurium-based orbitals. So the energies at the band extrema, the valence band extrema, are more or less the same. Calculations indicate at 0 Kelvin a band offset of 0.15 eV. But with thermal broadening, by the time you get to room temperature and above, these things more or less become equal in energy. And so if you have holes, they can transport through the material. They can find states across the material as well. Plus, the high mobilities give long mean-free paths. And these nanodots are, as I said, between 1 nanometer and 15 nanometers. So there's always states to go through, and also they're small enough that electrons can pass along easily. So if you're a hole, you may not notice that there is a second phase here because you find the right states to come across. If you're an electron, it's a different story. If you're an electron, you have to overcome this huge barrier. And indeed, when you dope these things n-type, you don't get the mobilities drop. You lose the mobilities because of the scattering that you see there. We have these two good effects. That you can combine them, you get a very high ZT at the 2%, closer to 1.7 or so, which is a record high number. That essentially tells you that this is a great approach to engineer the bands and the nanostructures such that you get maximum effect on the thermal conductivity, but not on the power factor. So after this, we looked at calcium telluride and barium telluride, and these are also good systems, not quite as high, but you can get about 1.5 or so on the 1.6 on the magnesium, and about 1.3 on the barium telluride. So they do a similar job. It's just that the strontium happens to be sort of the optimum system. So these are again high numbers. So let me skip a little bit here and move to the selenide system. There is some concern that whether there's enough tellurium to go around. Let's say if you went to, if you were to apply this and put them in every car, what would happen to the supply of tellurium and to its price? And there's a debate on that because no one knows what the annual production of tellurium is. But everybody agrees that it's probably limited. And so we have a motivation to look at tellurium-free systems. So we went to lead selenide. Lead selenide is similar but not identical to lead telluride. So here's how they compare electronic structure. I showed you this already. Here's the second band, and this is about 150 millivolts lower than this band. By the time you get to the selenide, it drops. So you may not have this effect, but this stays. This is similar, and that is similar. So we wanted to see how this will behave. So we went to lead selenide, and we wanted to see if we could add lead sulfide to lead selenide, whether we would get phase separation. But we found in the literature there was a phase diagram, and we found papers that said actually this particular system does form a solid solution. There is no phase separation between them. You see it here. There's no nucleation and growth region. There's no spinodal decomposition. So this was a legitimate solid solution. However, we nevertheless did it anyway. And we were surprised to see that, in fact, lead sulfide, lead selenide, it's not. It's an inhomogeneous system. It's, in fact, we found all kinds of nanostructures. Nobody had bothered to look before. It's generally inhomogeneous on the nanoscale, and we found the coherent nanostructures in these as well. This is a paper that came out last year, and here where the clue came from. We did make the samples. We made 10% samples between 8% and 12%, measured the thermal conductivity, the lattice thermal conductivity, and compared that to Clemens-Drabel theory of the solid solutions. And all the points came down below the theory. And so that clued us in that this may be also nanostructure. So we went to the TEM and found these images. They were not difficult to find. And you see here again the scales, 5 nanometer scale. You have nanostructures of different kinds. So lead sulfide appears to be precipitating out of lead selenide here as well. And again, earlier claims, after all, it is the myth of solid solutions. It's not a solid solution. It's also another nanostructure system. So you can take that, and we investigated the N-type system first. And here's just some data. I know it's a lot of data. Don't pay attention too much to the numbers, but this is just to show that you can put, it's well behaved from the doping perspective. You can put lead chloride, make it N-type. You can put indium, and indium can go into the lead side. Chloride can go into the selenide side, and you can put carriers in there. So essentially, you can control the number of carriers with these dopants, and here's the conductivities. They're all very high. This is a good thing to see. You can change the conductivity up and down. You can change the thermal power up and down. And of course, it goes opposite, right? The lowest electrical conductivity, yellow, has the highest thermal power, and vice versa. The highest conductivities have the lowest thermal power. That's how it's supposed to work. These are N-type systems, so you see the numbers here are negative. But you see here there's no sign of saturation all the way to 900 degrees. It keeps going up. And so that's a good thing because that tells you that the thermoelectric properties are likely to be good at high temperatures. By doing this optimization, you can get power factors that are very high, not as high as lead telluride, but nevertheless quite high for that. And then you can then optimize the sample. And so here's an example. The sample D, the green data, it has 12% lead sulfide. It's doped with lead chloride, and you get a ZT of about 1.3 at 900K. That is higher than regular N-type lead telluride, much higher, and almost as good as this nanostructured lead telluride, lead sulfide, only at a different temperature. So this is actually an exciting system because it's tellurium-free as well. And so our work continues with this. But what about even simpler, even less expensive system, like sulfur? So we went to lead sulfide. Now, the Russians did a lot of work in the 50s, in the 40s in lead sulfide. They found it was good enough of a thermoelectric. ZT, they maximized the ZT to about 0.4 at high temperature. And this was good enough for the Soviet regime to put lead sulfide in its 5-year economic development plan in the late 40s so that they can electrify the Siberia. And so you can have radios and stuff like that by burning wood and things like that. It never went anywhere because 0.4 of ZT isn't high enough. But Stalin would be happy if he was like today. So we said, can we nanostructure lead sulfide and see if we can make the thermal conductivity low? So we chose this system because we found a phase diagram that said bismuth sulfide is soluble in lead sulfide a little bit. And we thought, okay, if we can dissolve it here at this concentration and quench it and anneal it here, we will precipitate bismuth sulfide out and have a nanostructured system. What is the thermal conductivity of lead sulfide? Lead telluride, I said, is 2.2. Lead sulfide is 3.4. It's higher. So that's another reason why ZT is low. So we have more to fall from 3.4. These are the samples. You can make the samples. First, we had to look at the pure material just to reproduce what the Russians did. So this is pure, non-nanostructuring. We can add lead chloride, and we can raise the carrier concentration here in this line here. This line here is carrier concentrations. Lattice goes down because chloride is smaller. So everything behaves well. You can dope this. It's clean. And we did all the measurements here. This is so we did find. I'm not going to show you that data. We did find that the Russians were right. And then we went to this system with bismuth sulfide. And here, these are thermal conductivities. And essentially, we see a spectacular drop. This is the black data, is the pure lead sulfide. And we add 1, 2, 3%, all the way to 5%, and we can drop it way down. That's a spectacular drop. Percentage-wise, actually, is better than lead telluride. So we can do this with bismuth sulfide. We can do it with tin sulfide. We can do it with strontium sulfide, and we can do it with calcium sulfide. And this is the values we get. The solid lines are the values at high temperature. And you see these numbers are close, between 0.5 and 0.8. And the empty bars are the room temperature values. So what we are interested in is the solid bars, because these are the high temperature numbers. And these are very low for lead sulfide. Nobody has been able to decrease the thermal conductivity of lead sulfide that low. So the N-type samples then, we can do all this. You see how well behaved the system is. We add different amounts of lead sulfide, and we can have different conductivities, different thermal power. This is N-type. You see these negative numbers. And here's the ZTs. So the black is what the Russians made. Actually, we couldn't get 0.4, but it gets 0.4 at higher temperatures. Here's the samples. We have samples that are going to 0.8, and they keep rising with no sign of saturation. So this is, we get 0.8 for this sample, for the bismuth sample. This is the antimony. We get a similar number, about 0.8 as well. So this is a big jump in ZT for this system. Again, going into TEM, this is what you see. You see these coherent structures. It's nanostructured. It's not homogeneous. Here's the scale bar. So you have something between 2 and 20 nanometers, precipitated all over the place, bismuth sulfide. And the diffraction pattern here, these are different crystallographic directions. It's single crystal. So these are all coherent. We can find the elements there, and we can see that the nanostructures are rich in antimony or bismuth. So again, we have successfully nanostructured lead telluride and gotten very, very low thermal conductivities for that material. So then, because there was no sign of saturation, we were able, we deliberately got data up to 900 Kelvin. And you see, with specimens that are shown here that were spark plasma sintered, we were able to get data that are shown here that exceed 1. And this is remarkable for something like lead sulfide. Exceed 1.1 for the bismuth case, about 1.06 for the antimony case. So this is what the Soviets needed in the late 40s to make this worthwhile. But this is remarkable because this is the most inexpensive material you can ever have in thermoelectrics. There's magnesium silicide is another material people look at, but pound for pound, this is even cheaper than magnesium silicide. So the fact that we've been able to do this is, we think, significant because there's more upside, and it could have interesting applications. So with this, I'd like to close. This is what I call this is a multiple length scale problem. You start from atomic level, where you do some alloy scattering, and you do nanostructuring. It's a panoscopic view. In other words, if you take it from the atom all the way to the device, all length scales are important. All length scales have to be under control to get this to work. I concentrated in the top 3 all the way to the nanostructure. So everybody who is doing thermoelectrics today are looking at nanostructuring. because everybody's convinced that this is the way to go to achieve the lowest thermal conductivities. This part, the interfaces to make contacts to the devices are on another scale. Those have to be under control. That's not part of our project. And of course the devices themselves. And so this is a very interesting project for many disciplines and many types of approaches to get this to get this to work. Here I saw the sort of the top thermoelectric materials today. It's a little bit out of date because some of the materials I showed you are not even here. But the top now, we are very close to 1.7. This is the N-type systems. This is the P-type systems. We're about 1.7 or so, 1.8. And this is good enough for some of the applications that I showed you earlier. That's why I call this a paradigm shift, because we switched from looking at single-phase compounds into looking at inhomogeneous mixtures at the nanoscale. To conclude, this nano is good. These are bulk materials, but they are nano. And they work because they are nano. So nanostructuring reduces the thermal conductivity. Endotaxy is good for to enable phonon scattering, but also to allow electron flow, so you don't have defects. The lowest thermal conductivity that we have gotten is about 0.4 to 0.6. There's a little bit more downside on that, maybe 0.25 or so. Then it's going to stop. I don't think, even if it goes to 0, we can get maybe the ZT of about 2.2 or 2.4, and then we're done. If we want ZTs of 3 or 4, we have to work on the power factor. We need to get higher power factors to get into that territory. And so the large power factors in the next few years, 3 to 5 years, then the name of the game could be maximization of the power factor. And that's where we need guidance from fearless theorists who can tell us how we might do that. It doesn't have to work. All it has to do is be plausible, and we'll figure it out. So in any case, all this was funded by, originally by ONR, but lately in the last 3 years by our EFRC, Energy Frontier Research Center, by DOE, which is joint between Michigan State, Northwestern, Michigan, Wayne State, and Ohio State. And I'm grateful for that. And I will open it up for questions.
So I'm using this microphone because we're videotaping this. And so there are two things to say. One is don't talk until you have the microphone. And the second is that you should realize that whatever you're saying will be recorded for posterity. Can I take the prerogative of asking the first question? It's interesting because what you're doing is you're exploiting the nucleation of these phases, and so it occurs to me that it would be really interesting to take a given composition and play with nucleation and growth rates to see how that affects, in a systematic way, because that will change the size and the distribution of the secondary phase. Are you trying to do that in a systematic way?
Yeah, this is a very good point. And yes, we are, but we haven't done it yet. This is what my colleague Vinay Dravid is badgering me to do with my students, to do the systematic study and get the different sizes by doing different annealing times.
Right.
And we will be doing that. This would be great because it will give us this other dimension of the size, which we don't have a good control over.
Right.
So I don't know what would happen, but this is something that is in our plan.
Okay. Other questions?
Thank you. So, for potential practical applications of these devices in waste heat and similar, what is a realistic range for the temperature? Because I see that at lower temperatures, where much of the waste heat is available, the ZTs are low. And is there any possibility for increasing those at low temperatures?
So for the automobile applications, the temperature of interest is well within these temperatures, is between 500 and 800. This is where you want to be in a car or in an over-the-road truck. So we're okay with that. It's in the ballpark. 900 is a little bit too high, but not 800 and 700. So this is the right ballpark. Also, the efficiency of these things can be raised by doing what they call segmentation. So at low temperature, you can use bismuth telluride, and you can join it together so you can have a leg, half of which is bismuth telluride that has high ZT at the cool end, and the other half could be something like this that has high ZT on the larger end, and you can raise the overall ZT and get a boost there as well. But nevertheless, these temperatures, to answer your question, are fine. Anywhere from 550 to 800 is what we're looking at. Most people are looking.
And you're at the range of ZT there that is useful? I think that
Yes,
was the other
because
part.
as you see here, we're getting into this 1.7, 1.8, and so it is in this area. That's the correct range, and that's stable.
Other questions? Yeah, okay.
Thanks. I just had a quick question. I was wondering what kind of instrumentation you use to make your measurements of the thermoelectric properties.
Okay, yeah, this in the old days, and the old days being 10 years ago, people had to build their own instrumentation, their own thermal power, their own thermal conductivity, and so on. And in those days, it was an issue was people would have 3 different systems, and they will make 3 different measurements on the same sample. And that's not the ideal. You want to make all measurements at the same time, at least thermal power and conductivity. So today, it's a good time to do thermoelectrics because you can buy commercially available measuring instrumentation that has been tested and used so much that it's, everybody now believes that the instrumentation is good and it gives good numbers. There's a couple of companies, and we have a few of their instruments, that sell a device that can do measurements from room temperature to about 1,000 degrees C simultaneously of these 2 measurements. And because of the community has done a lot of round robins and a lot of self-testing, by exchanging samples and so on, that we now we're past the point where we say, well, are these numbers right or not? We pretty much trust them. So today, it's a good time to do this because you don't have to be your own instrument builder to do this.
Other questions? Okay, well, if